Hello students, in this video we'll try to see solutions for previous year NEET questions, and we'll be concentrating on the topic called thermodynamics. So before going inside the questions, let us have a statistical analysis about the previous year question papers, like which importance were given for what are all the topics under thermodynamics. So if you see, in the last 33 years, questions were coming from different topics from thermodynamics. So about 39% of questions were coming from work, internal energy, first law of thermodynamics, and 28% of questions were coming from thermodynamic processes, and 29% were coming from heat engine refrigerator, and 2% of questions were coming from second law of thermodynamics, and 2% were coming from reversible and irreversible process. So this is what the scenario in the last 33 years, and you can see from the statistical report that around 39% were coming from work, internal energy, and first law of thermodynamics. So if you just have a look, the last two topics, they were not giving prior importance, but first three topics were given equal importance. More or less it was having an equal importance of around 30%. So you need to concentrate more on all these particular topics called work, internal energy, first law of thermodynamics, thermodynamic process, heat engine, and refrigerators. And if you see the NEET analysis for the past 8 years, you can just have a look here. They have stopped asking questions from the last two parts. Okay, second law of thermodynamics and reversible and irreversible process. And they are particularly concentrating on work, internal energy, first law of thermodynamics, thermodynamic process, and heat engine refrigerator. So around 38% still work, internal energy, and first law of thermodynamics were holding the highest percentage of questions. Around 38% of questions were coming from this particular topic, and next, heat engine and refrigerator were having a higher percentage. Around 33% of questions were coming from this particular topic, and 29% were coming from thermodynamic processes. So again, if you have a look at this particular statistical report, we are able to find out that majority of the questions were coming from the first topic and from the third topic, and equal importance were also given to the middle one, the thermodynamic process. So having a look at this, we can come to conclusion that maximum number of questions will be coming from this particular three topics. So in this video, I'll try to solve the previous NEET question papers, which will be covering all these three topics. So we'll try to solve different kinds of problems which covers all these three topics. So let us go on with the first question. 1 gram of water of volume 1 centimeter cube at 100 degree Celsius is converted into steam at same temperature under normal atmospheric pressure. So it is equivalent to 1 into 10 power 5 Pascal. The volume of steam formed equals 1671 centimeter cube. If the specific latent heat of vaporization of water is 2256 joules per gram, what is the change in internal energy is? So they want us to calculate the change in internal energy. So this question you can solve it using the first law of thermodynamics. So you all know what is the first law of thermodynamics. Del Q is equal to del U plus del W. So ml is equal to del U plus P into V stream minus V water. Okay, so it is a volume. So already they have given the volume of stream as 1671. You're going to substitute here, minus volume of water is 1. So you're going to substitute it in the formula 1, because m is 1 gram of water they have mentioned. So 1 into L is 2256. Here they are given the latent heat 2256 equal to del U plus the pressure they given it as 1 into 10 power 5. So you can put it as 10 power 5 into 1671, because the volume stream here they are given it as 1671 minus 1 into 10 power minus 6. Okay, so if you just solve this, you will be getting 2256 equal to del u plus if you solve this, you will be getting it around 1670, and here on 10 power minus 5, sorry, minus 6 into 10 power 5 is 10 power minus 1, so this will become 167. So del u will become 2089 joules. So the correct answer is option number 3, 2089 joules. So that is the change in internal energy. So here they are saying that they are trying to convert 1 gram of water of volume 1 centimeter cube at 100 degrees is converted into steam. That is, they are heating the water uh, at the same temperature under normal atmospheric pressure. So the volume of steam formed equals 1061 centimeter cube. So, and they have given the specific latent of vaporization of water, and they are telling us to calculate the change in internal energy. So it is a very simple question. You're just going to apply the first law of thermodynamics. Del Q equal to del U plus del W. Del Q is ml and del U only you have to calculate. Del W is P into V stream minus V water. Volume of the water, volume of the steam minus volume of the water. And you're going to substitute the values, whatever they have given. Okay, so if you just substitute and if you solve it, you will be getting the del U value as 2089 joules. So the volume of the stream they have given it as 1671, and volume of water is 1, and latent heat is 2256. You're going to substitute and you're going to find. So the correct answer is option number 3. Okay. So let us move on to the next question. A sample of 0.1 gram of water at 100 degrees Celsius and normal pressure 1.013 into 10 power 5 requires 54 calorie of heat energy to convert to steam at 100 degrees Celsius. If the volume of the steam produced is 167.1 cc, the change in internal energy of the sample is, they want us to calculate the change in internal energy. So first you need to calculate the change in volume, that is del V. So change in volume you have to first calculate, which is equivalent to del V. So which is equal to V stream minus V omega. Okay, so here they have given the value of stream, the volume of stream as 167.1 to 10 power minus 6 minus the volume of water. Okay, so it is 0.1 into 10 power minus 6, 0.1 to 10 power minus 6. So this will become 167 10 power minus 6 meter cube. So this is the change in volume. Now work done in the process is calculated by del W is equal to P into del V. So here as per the question they have given the pressure as 1.013 into 10 power 5. So you are going to substitute it here, 1.013 10 power 5 into 167 into 10 power minus 6. Okay, so if you solve this, you will be getting it as 16.92 joules. So from the first law of thermodynamics, we know that del Q is equal to del U plus del W. So change in internal energy is calculated by del U is equal to del Q minus del W. So we are using the same formula what we have used in the previous problem. So del Q, you know, it is 54 into 4.18. So you're going to put it here, 54 into 4.18 minus del W you have calculated here, 16.92. Okay, so if you solve this, you'll be getting it as 2572 minus 16.92. So ultimately, if you solve this, you'll be getting it as 208.8 joules. Okay, so the change in internal energy is 208.8 joules. So the correct answer is option number 2, 208.7 joules. Okay, so the change in internal energy of the sample is 208.7 joules. So it is also a very simple question where you are trying to make use of the same formula, the first law of thermodynamics, and you are trying to solve it, and you are able to find out the change in internal energy. First, you need to calculate the change in volume, and then you have to calculate the work done. Okay, work done, and then you need to uh, find out what is the value of uh, del q, and you are going to substitute it. Okay, so it's a very simple problem only. So let us move on to the next question. A gas is compressed isothermally to half its initial volume. The same gas is compressed separately through an adiabatic process until its volume is again reduced to half. Then what happens? So here they are saying a gas is being compressed isothermally to half of its initial volume. The same gas is compressed separately through an adiabatic process until its volume is again reduced to half. So what happens to it? So they given us four options. Compressing the gas isothermally or adiabatically will require the same amount of work. Which of the case, whether compression through isothermal or through adiabatic process, requires more work will depend upon atomicity of the gases. And compressing the gas isothermally will require more work to be done. Compressing the gas through adiabatic process will require more work to be done. So here, if you just have a graph between P and V, so you know this is adiabatic process, and whereas this will be for the isothermal and adiabatic process. Okay, so it will be like this. So to reduce it to half, so you are trying to compress the half, the volume. You are trying to reduce the volume to half. So in adiabatic process, if you see, the work done is given by the area under the curve. While compressing the gas adiabatically, the area under the curve is more than for the isothermal expression. So you know that it's just a graph between the pressure and volume, and for isothermal process, if you see, the area of curve is very less in comparison with the adiabatic process. So the area of the curve will give you the work done. So compressing the gas through adiabatic process will require more work to be done is the correct answer for this question. Okay, so you require a more amount of work to be done for compressing a gas through adiabatic process rather than an isothermal process, which can be evident from seeing the graph, where the area under the graph for isothermal process is very small in comparison with the area under the graph for an adiabatic process. So work done is given by the area under the graph. So the correct answer is option number 4. Okay, that's a very simple question. You're just going to use the graphical representation. You are trying to solve it, and the same thing can be used for the next question also. An ideal gas is compressed to half its initial value by means of several processes. Which of the process results in the maximum work done on the gas? So again, a similar kind of thing is there. You can see you'll be having the pressure and the volume on either sides. You'll be plotting a graph like this. Okay, so for adiabatic, it will be like this, and for isothermal, it will be like this, and for isobaric, it will be like this. Okay, so if you see, Again, this is adiabatic, isothermal, isobaric. Okay, so this is V1 by 2, and on the y axis you'll be having the pressure. So if you see here, the work done is again area under the curve, and the work for isochoric will be 0. Isochoric will be 0. So if you see from the graph, the work done for adiabatic is greater than the work done for isothermal, and it is greater than the work done for isobaric. Okay. So here you can see which of what they are asking is which of the process results in the maximum work done on the gas. So since the work done for adiabatic is greater, the correct answer is option number 2, adiabatic. So this is also a very simple problem. We are just going to use this graphical representation, and you are going to find out the area under the curve, which one has the highest maximum value under area under the curve, and you can see that the adiabatic process is having a maximum area. So the maximum area means that much amount of work is required to be done. So the maximum work to be done on the gas is through adiabatic process. The correct answer is option number 2. Okay. So let us move on to the next question. Figure below shows two paths that may be taken by a gas to go from a state A to state C. In process BC, 100 joules of heat is added to the system. The heat absorbed by the system in the process AC will be. So here they are given a graphical representation. So they are saying that two paths that may be taken by a gas to form a state A to C. Okay, from A to C it is going to go. In this process, BC, 100 joule of heat is added to the system. So the heat absorbed by the system in the process will be. So here Q ABC is equal to QAC plus work done by ABCA. Okay. So WABCA is given by area of PV graph, so which is equal to half into AB into BC, because it's a triangular graph, so you'll be getting half into length into breadth. Sorry, half into two sides of the triangle. Okay, so half into AB into AC. So work done is given by 500 is equal to, because here you are having 2 into 10 power 4 Pascal, you're going to substitute that here. So if you substitute that, you'll be getting is equal to QAC plus half into 4 into 10 power 4, because AB is 4 into 10 power 4 into, so this difference is 2 into 10 power minus 3. Okay, so if you solve this, you'll be getting QAC is equal to 500 minus 40, which is equal to 460 joules. So the correct answer is option number 3, 460 joules. So the heat absorbed by the system in the process AC will be 460 joules. Okay. So let us move on to the next question. 1 mole of an ideal diatomic gas undergoes a transition from A to B along a path AB as shown in the figure. The change in internal energy of the gas during the transition is, so here the change in internal energy del U is equal to P2 V2 minus P1 V1 by gamma minus 1. So which is equal to 2 into 6 minus 5 into 4 divided by 7 by 5 minus 1. Okay, because the gamma value for diatomic gas is 7 by 5. So you are going to substitute it there here. and you will be getting the final value as minus 20 kilojoules. Okay, so it is a very simple question. You are going to find the change in internal energy of the gas during the transition, which is equal to minus 20 kjoules. So the correct answer is option number 2. Okay, so let us move on to the next question. A thermodynamic system undergoes cyclic process ABCDA as shown in the figure. What is the work done by the system? So here you can see they've plotted a graph between pressure and volume. You are having a ABCDA plot ABCDA, which is a thermodynamic system which undergoes a cyclic process. Now they want us to calculate the work done by the system. So W B C O B. First you are calculating for this triangle. The work done for BCOB. So which is equal to minus area of triangle BCO. So which is equal to minus P naught V naught by 2. Okay, why it is minus is 3P naught minus 2P naught. So it will become minus 2P naught minus 3P naught. So it will become minus P naught into V naught by 2, half into the two sides of the triangle. So this is 2 V naught minus V naught. So it will become V naught. So minus P naught into V naught by 2. Similarly, we will be doing it for the second triangle WAODA. So again same thing, area of triangle AOD. So this will become P naught V naught by 2. So the total work is given by W of AODA plus W of BCOB. So it become P naught V naught by 2 minus P naught V naught by 2. So both will cancel each other and the final value will be getting 0. So the total work done in this particular thermodynamic system is 0. Okay, this is also a very simple problem. Just you are going to find out the area of the triangle. So ultimately, if you take any kinds of a PV graph, the area of the graph, area under the curve will give you the work done. So that's what we are done here. You are calculating the area of the first triangle, this one, and you are calculating the area of the second triangle, this one, and you are taking the sum of these two. So the resultant sum is 0. So the total work done here in this particular case is 0. Okay, so let us go to the next question. A gas is taken through the cycle A to B, C to A as shown. What is the best work done by the gas? Okay, same kind of a question. They want us to find out the net work done by the gas. So the net work done again is given by W is equal to area of ABCA. Okay, so same thing, which is equal to half into this value is 7 and this value is 2. So 7 minus 2 you have into 10 power minus 3, 10 power minus 3 into this value is again 2 and this one is 6. So 6 minus 2 into 10 power 5. So that is the pressure value. So 10 power 5. So you will be getting it as here it is P 10 power 5 Pascal. Okay, so that's why I'm putting this 10 power 5 here. So half into 5 into 10 power minus 3 into 4 into 10 power 5. So if you solve this, you will be getting it as 10 into 10 power 2 joules. So it is around 1000 joules. Okay, so the correct answer is option number 4, 1000 joules. So the net work done by the gas is 1000 joules. Very, very simple questions. So if you see all these questions where you're trying to calculate the work done, all are based on the same formula. like it's not a kind of a formula. You're going to find out the area of the curve. Okay, so most of the questions they'll be giving the triangle, so you can easily know the formula of the triangle. You can find out the work done easily by just substituting the values whatever they are given in the question. So let us move on to the next question. A thermodynamic system is taken through the cycle ABCDA as shown in the figure. Heat rejected by the gas during the cycle is. So here they have given a figure where you can see the thermodynamic cycle is taking place between A, B, C, D, A. They want us to find out how much heat is being rejected by the gas during the cycle. So you all know the first law of thermodynamics, del Q is equal to del V by plus W. So in a cyclic process, what happens is your del U will become 0. So the internal energy is a state of a function. In a cyclic process, work done is also equivalent to the area under the cycle, and it is positive if the cycle is clockwise, and it is negative if it is anti-clockwise. Okay. So the heat absorbed is given by del Q is equal to Q is equal to minus 2V into P. So this will become minus 2P. So this is the heat absorbed. So the heat rejected will become 2, the opposite of that. Okay. So the heat absorbed is minus 2V, the heat rejected will be plus 2V, 2PV. So the correct answer is option number 1. That is the amount of heat being rejected by the gas during the cycle as shown in the figure. Okay. So it is also a very simple question where you are using the graphical representation to calculate the amount of heat being rejected by the gas. So let us move on to the next question. The PV diagram for an ideal gas in a piston cylinder assembly undergoing a thermodynamic process is shown in figure. The process is, so here they are given a thermodynamic process where uh, they have shown a PV graph. Okay, the pressure versus volume graph. And if you remember, I have drawn one graph in the earlier stages. Okay, for isobaric. So uh, like I showed a little bit curve. So for adiabatic process, it will be like this, and for isothermal, it will be like this, and for isobaric, it will be like this. Okay, so it will be kind of a linear line where if you take a isobaric process, what happens is the pressure remains same when you are trying to change the volume. So it will be like a linear line. So if you see the same thing here on seeing this particular graph, you can see that the pressure seems to be same from the initial state to the final state. Only the volume seems to be changing, but the pressures seems to be changed. So we call this process as an isobaric process. Okay, where the pressure of the gas seems to be same in an ideal position. So automatically the volume used to changes. So this process we called as isobaric. So from seeing the graph, we can easily identify that it resembles to an isobaric process. So as per the question, the PV diagram for an ideal gas in a piston cylinder assembly undergoing a thermodynamic process is shown. So when you see this thermodynamic process, it resembles an isobaric process. So the correct answer is option number 4. Okay. So let us move on to the next question. Two cylinders A and B of equal capacity are connected to each other via a stopcock, and A contains an ideal gas at standard temperature and pressure. B is completely evacuated. The entire system is thermally insulated. The stopcock is suddenly opened. What is this process? So, a change in pressure and volume of a gas when no heat is allowed to enter or escape from a gas is an adiabatic process. Okay, so adiabatic process means there will be a change in pressure and volume of the gas when heat is not allowed to enter or escape from the gas. So it also takes place very rapidly as described in the question. You can see in the question they are having two cylinders A and B of equal capacity which are connected to each other by a stopcock. You are having a stopcock in between which is stopping the connection between the two cylinders. And one contains an ideal gas at a standard temperature and pressure, and B is completely evacuated, so it is empty. The entire system is thermally insulated also. So this word thermally insulated means heat cannot be entering or heat cannot escape from it. Okay, so the stopcock is suddenly open. What happens? There will be a change in pressure and volume because from one side to other side the gas will start moving. So there will be a sudden change in the pressure and volume when there is no heat flow or heat is being escaped from the gas because it is thermally insulated. So this process we call it as adiabatic process. So the correct answer is option number 1. So the process is adiabatic, where a change in pressure and volume of the gas is being taking place without any heat which is being allowed or to enter or to escape from the gas, and it also takes place so rapidly as described in the question. So the correct answer is option number 1, adiabatic process. So let us move on to the next question. In which of the following process heat is neither absorbed nor released by a system? Isobaric, isochoric, isothermal, or adiabatic? So it's also a similar explanation whatever I gave it for the previous question. I said no, like in an adiabatic process you will not be having, it will not be allowing heat to enter or to escape. So similarly here in an adiabatic process what happens is exchange of heat del Q will become 0. So the correct answer is option number 4, adiabatic, in which heat is neither absorbed nor released by a system. So the correct answer is option number 4. So the next question is, a monoatomic gas at a pressure P having a volume V expands isothermally to a volume 2V, then adiabatically to a volume 16V. The final pressure of the gas is taken by. So here they are telling us to calculate the final pressure. So and here gamma value they are given it as 5/3. So first initially it expands isothermally. So for isothermal expansion, PV is equal to P2 into 2V, or P2 is equal to P by 2. So this V and V will get cancelled. This is for isothermal expansion. And next thing is for adiabatic expansion, you will be getting it as P2 V2 gamma is equal to P3 V3 gamma. So P by 2 into 2V 5/3 is equal to P3 into 16V 5/3. Okay, so P3 is equal to P by 2 into 2V by 16V per 5/3. So if you try to solve this, you will be getting it as P by 2 into 1 by 8 per 5/3, which is equal to P by 64. So the correct answer is option number 3, P by 64. The final pressure of the gas is given is equal to P by 64. So this is also a very simple question where first you are calculating the pressure for isothermal expansion and then you are calculating it for adiabatic expansion. So you are going to substitute the value of the isothermal pressure in the adiabatic expression and you are going to find out the final pressure P3 value, which is equivalent to P by 64. Okay. So let us move on to the next question. During an adiabatic process, the pressure of a gas is found to be proportional to the cube of its temperature. So the ratio of Cp by Cv for the gas is, so for an adiabatic process, P is directly proportional to T per gamma minus 1. And here they are given it as P is directly proportional to T per cube. So automatically gamma by gamma minus 1 is equal to 3, or gamma is equal to 3 gamma minus 3, or minus 2 gamma is equal to minus 3, or gamma is equal to 3/2. So it's a very simple question. For an adiabatic process, P is equal to V is direct proportional T per gamma minus 1. But here in this question, the pressure of the gas is found to be proportional to the cube of its temperature. So what will be the ratio of Cp by Cv they have asked? So it is equal to gamma is equal to 3 by 2. So just you are going to substitute it in this particular formula and you are going to find out what is the gamma value. Okay, so it is again a very simple question. The correct answer is option number 4, 3 by 2. Okay, so let us move on to the next question. The efficiency of a Carnot engine depends upon. So efficiency of a Carnot engine is given by eta equal to 1 minus T2 by T1 into 100 percentage. So it depends mainly on temperature of source T1 and temperature of source T2. Okay, so it depends on both the parameters. Depends both that is the efficiency is given by 1 minus T2 by T1 into 100%. So it depends on T2. T2 is the temperature of the sink and T1 is the temperature of the source. So the correct answer is that it depends on both the temperatures of the source and sink. So the correct answer is option number 3, where the efficiency of the Carnot engine depends on both the temperatures of the source and the temperature of the sink. So let us move on to the next question. The efficiency of an ideal heat engine working between the freezing point and the boiling point of water is. So they are telling us to calculate the efficiency of an ideal engine which is working between the freezing point and boiling point of a water. So again you are going to make use of the same formula, equal to 1 minus T2 by T1, which is equal to T1 minus T2 by T1. So it is 100 divided by 373. Okay, so if you solve this, you will be getting it as 0.268 or it is 26.8 percentage. Okay, because you will be having 100 here into 100 percentage, so it is 26.8 percentage. So the correct answer is option number 1. A very simple problem. Just you are going to substitute the same formula for calculating the efficiency of the Carnot engine, and T1 minus T2 is 100 and temperature of the source will be 373, so it will become 0.268 into 100 percentage, it will become 26.8 percentage. So the correct answer is option number 1. So let us move on to the next question. A Carnot engine having an efficiency of 1 by 10 as a heat engine is used as a refrigerator. If work done on the system is 10 joule, the amount of energy absorbed from the reservoir at low temperature is. So since beta is equal to Q2 by W, which is equal to 1 by eta by eta, Q2 by 10 is equal to 1 minus 0.1 by 0.1. Okay, so here they are given the efficiency 1 by 10, so efficiency you are putting it as 0.1, 1 by 10, and work done is 10 joule, so W is 10, so you are putting it here. Okay, so Q2 will become here 0.9, so and this 0.1 it is going to the numerator, it will become 9 into 10, so the correct answer is 90 joules. So Q2 is 90 joules. So the amount of energy absorbed from the reservoir at low temperature is 90 joules. The correct answer is option number 2. It is also a very simple problem. Now let us go on to the next question. A refrigerator works between 4 degrees Celsius and 30 degrees Celsius. It is required to remove 600 calories of heat energy every second in order to keep the temperature of the refrigerator space constant. The power required is. So here they are saying a refrigerator is working between 4 degree and 30 degrees and it requires around 600 calories of heat every second. So in order to keep the temperature of the refrigerator space constant, how much power is being required? So here again same formula, Q2 by W is equal to T2 by T1 minus T2, and here T2 is 4 degrees Celsius, so which is equal to 276 Kelvin, and T1 is 303 Kelvin. So Q2 is 600 calories. Okay, so 600 divided by W is equal to 277, 303 minus 277, or W is equal to 600 by 10.65. Okay, so you're just going to put W is equal to 600 by 10.65 because you're trying to solve this, and this, if you solve this, you'll be getting it around 10.65. so just you are cross multiplying it, and you'll be getting the W value as 56 calories. Okay, this much amount of work is being done, but we need to calculate the power. So P is equal to W by T, which is equal to 56 by 1 into 4.2. okay, because here telling 1 calorie as 4.2 joules. Okay, so you are converting it, and for every second, so T is 1, so the power will become 236.5 watt. So the correct answer is option number 1. So the power required to maintain or to keep the temperature space constant is 236.5 watt. Okay, so it's also a very simple problem. So let us now move on to the next question. The coefficient of performance of a refrigerator is 5. If the temperature inside the freezer is minus 20 degrees Celsius, the temperature of the surrounding to which it rejects heat is. So here they are given the beta value as 5 and T2 value is minus 20 degrees Celsius. So it is 20 plus 273, and your T2 will become 253 Kelvin, and beta is equal to T2 by T1 minus T2. So T1 is the temperature of the surrounding and T2 is the temperature of the source inside temperature. So 5 is equal to 253 by T1 minus 253. So if you solve this, you will be getting 5 T1 minus 1265 equal to 253. T1 is equal to 1518 divided by 5, which is equal to 303.6 Kelvin. So which is approximately equal to 30.6 degrees Celsius, or approximately equal to 31 degree Celsius. So the correct answer is option number 2. So again, it is a very simple formula. They have given the coefficient of performance of the refrigerator as 5, and temperature inside the freezer they are giving it as minus 20 degrees. So they want us to find out the temperature around the surrounding. So they are given the beta value, they are given the T2 value, you want to find out the T1 value. So you know beta is equal to T2 by T1 minus T2. So you are going to substitute in this formula and you are going to find out the temperature of the surrounding, which is equivalent to 31 degrees Celsius. Okay, so let us move on to the next question. A Carnot engine having an efficiency of 1 by 10 as heat engine is used as a refrigerator. If work done on the system is 10 joule, the amount of energy absorbed from the reservoir at low temperature is. So here same formula, beta is equal to Q2 by W, which is equal to 1 minus eta by eta. So Q2 by the work done is 10 joules, so you are putting 10, and here the efficiency they are given it as 1 by 10, so it will become 1 minus 0.1 by 0.1. So Q2 will become 0.9 divided by 0.1, which is equal to 9. So 9 into 10, so this will become 90 joules. So it is also a similar question which we have solved earlier. It's kind of a same question which we have solved earlier. So The correct answer is option number 2. Okay, so the same question has been repeated in NEET 2015, and also it has been repeated in the same way in NEET 2017. Okay, so where we are trying to use the same formula. So the next question is, when 1 kg of ice at 0 degrees Celsius melts to water at 0 degrees Celsius, the resulting change in its entropy, taking latent heat of ice to be 80 calories per gram is. So here this question is based on the concept of second law of thermodynamics, where they given Q is equal to m ice into L ice. Okay, so here the weight they have given it as 1 kg into, and the latent heat they have given it as 80 calorie per gram. Okay, so it is equal to 1000 grams into 80 calorie per gram, which is equal to 8 into 10 power 4 calorie. Now they want us to find out the change in entropy. So change in entropy is given by del S is equal to Q by T, so which is equal to 8 into 10 power 4 divided by 273. So if you solve this, you will be getting it as 293 calorie per Kelvin. So the correct answer is option number 4. So the change in entropy, resulting change in entropy is given by 293 calorie per Kelvin. So it is a very simple problem where you are trying to use the second law of thermodynamics concept, where Q is equal to m into L, and m is the mass of the ice, which is equal to 1 kilograms, which they are given here, and L is the latent heat, which they have given it as 80 calorie per gram. So you are going to substitute and you are going to find the Q value, and change in entropy is given by Q by T. So you are going to substitute Q, 8 into 10 power 4 by 273, you will be getting it as 293 calorie per Kelvin. Okay, so let us move on to the next question. Which of the following processes is reversible? So transfer of heat by radiation, electrical heating of a nichrome wire, transfer of heat by conduction, and isothermal compression. So if you see here, transfer by heat, all the 4 processes, we can find out that transfer of heat by radiation is not a reversible process. So I mean, heat is being transferred through radiation, again it cannot revert back. And second thing is, electrical heating of a nichrome wire also is not a reversible process. And third thing, transfer of heat by conduction is also not a reversible process. But the fourth one, isothermal compression, is a reversible process. So we have few examples for that. You can take a Carnot cycle, you can take a heat engine and all, which is having a isothermal compression, and which is also having it is a reversible process. So the correct answer is option number 4, isothermal compression, which is a reversible process. We can state few examples like Carnot cycle, heat engine and all. Okay, so I think this video would have been useful for you to understand the basic concepts of thermodynamics, and as I was saying, you need to concentrate more on 3 particular topics called work, internal energy, first law of thermodynamics, thermodynamic process, heat engine, refrigerators. Okay, so maximum number of questions will be covering all these 3 topics, and I've also solved problems which are relevant to these 3 topics, and I have solved the recent question papers and the questions which are asked frequently. So I hope this video would have been helpful for you to understand the basic principles of thermodynamics, and it will be easy for you to understand how to solve the problems. And I wish you all a good luck for your examinations. Kindly prepare well and perform your exam in a better way. So all the best, and thank you for watching this video.